Good afternoon, class, and welcome to Chapter 1, The Foundations of Chemistry. Chemistry is a science, and a science is at heart all about finding things, finding information about the world. And how do we do that? Well, we do that by conducting experiments. And in order to conduct experiments, one must take measurements. So that's the first thing we're going to start with is measurements. All measurements contain three important pieces of information: the size or magnitude, i.e. the number, the standard or comparison, which is the unit, and an indication of uncertainty. All three pieces are critical for any measurement. But let's start with the size or magnitude, i.e. the number portion of your measurement. We can write measurements in different ways, such as in decimal form or scientific notation. Scientific notation is used a lot in chemistry, particularly because we deal with some very large numbers, and they would be very awkward and inconvenient to write them out. For example, one number that we're going to come in contact with in chemistry is this one, 6.022 times 10 to the 23rd. If we are not comfortable putting this into scientific notation, when we use it, we would have to write this out. Writing this number out is a little bit ridiculous. Now, can you imagine writing this number out every single time you wanted to use it? No. So, we're going to have to learn to use scientific notation. And I know that it may have been a while for some of you, so I'm just going to do a quick refresher on how to write numbers in scientific notation and how to take numbers out of scientific notation. Okay, so the maximum weight of a Boeing 777 at takeoff is 298,000 kilograms. That's a pain in the butt to write every time you want to write it. So we came up with a shorthand. The shorthand is scientific notation. In scientific notation, we take a number, like 298,000 kilograms, and we take the decimal point and we place it immediately after the first number that is not 0 in our number. So the first number not 0 is this 2 here. So we have 2 decimal point, 98. Then we write times 10, and we raise this 10 to a power. That power is determined by the number of places you moved your decimal point. So we put it here. It was originally here. How many places did we move it? 1, 2, 3, 4, 5. So therefore our exponent is a 5. Our exponent is a positive 5 because the number we were placing into scientific notation was larger than 1. What if we're working with a very small number, i.e. if you're a biologist looking at mosquito populations? And the weight of a mosquito in kilograms is 0.00000025 kilograms. So, again, this would be very awkward and inconvenient to write every single time you needed to discuss the weight of your mosquitoes. So what we're going to do is we're going to put this into scientific notation. The decimal point is going to go immediately after the first number that isn't 0. This 2 right here is not a 0. So that is where our decimal point is going to go. And of course we keep the 5. Now we want to see how many places did we move that decimal point. 1, 2, 3, 4, 5, 6 places. So times 10 to the 6. However, because this number that we're placing into scientific notation is less than 1, our exponent is negative. And then the final step is to keep your unit. These two things are the same thing. Okay? They're just written in different ways. And these two things are the same thing. Again, they're just written in different ways. Okay, so let's try a couple more. Example 1 says convert 578,400 into scientific notation. Our decimal point is going to go immediately after the first number that isn't 0. In this case, that would be a 5. So we have 5 decimal point 784 times 10. Now, how many places did we move our decimal point? So we had a 5, 7, 8, 400. We put the decimal point here. It was originally here. We moved it 1, 2, 3, 4, 5 places. 10 to the 5th. Because this number is greater than 1, our exponent is positive. So our final number is 5.784 times 10 to the 5th. Our second example says convert 0.00000062 into scientific notation. So again, what are we going to do? We're going to place our decimal point immediately after the first number that is not 0. So we have 6.2 times 10. Now, we can see that this number is less than 1, so our exponent is going to be negative. Okay. And how many places did we move this? 1, 2, 3, 4, 5, 6, 7, 8 places. This is going to be 6.2 times 10 to the negative 8 in scientific notation. So please become comfortable with this notation. You will be using it a lot this semester. There are also some videos available for you to watch if you still need extra help. Okay, so let's talk about the SI system. In the sciences, we use the SI system, which is an updated version of the metric system. So here's the thing. Scientists all across the world work together, and it's really important that we're all using the same units. Okay? We want to be able to compare our work directly to each other, so it's important that everyone agrees to use the same rules, the same units. Here in America, we're one of the few countries that uses the American system of measurement, i.e. we use things like inches, feet, we use gallons, we use cups, we use ounces. Most of the rest of the world uses the metric system. There's a reason for that, a really good reason for that. And the reason for using the metric system is that it's all based on powers of 10. So if you want to convert from inches to feet in our system, you have to use multiples of 12. In the metric system, it's 10. If you're going, say, ounces to pounds, you're talking about a unit of 16 instead of 10. So it's really important to have a nice, easy, simple system that everyone can use. If you're going into the sciences, if you're going into medicine, if you're going into engineering, it's going to be really important for you to be comfortable with the metric system, and by extension, the SI system. So we are going to use this system all semester long. If you take Chem 2, you'll use it all the next semester. Take Physics, you'll use it. So let's get comfortable with it. First, there are several common prefixes in the SI system. Some of them you will memorize just by using them all of the time. However, of the common prefixes, there are 4 that I expect you to be able to use immediately. Memorize them. You must be very comfortable with these 4 units. They are milli, centi, deci, and kilo. Milli, centi, deci, and kilo. And we're going to see how to use these. But these 4 conversion factors right here are very important. And you must know how to use them without looking at your notes. Okay, so you see up here on the left-hand corner, there is a metric conversion chart. And we're going to use this chart to see how we can quickly and easily convert between metric units. But in order to use this chart, we first need to talk about the base unit. Okay? There are several base units which are really important. Length is measured by the meter. Mass is measured by the gram or kilogram. Time, we use the second. Temperature, we use Kelvin or Celsius. And amount, which we're going to get into in chapter 3, we are going to use the mole. Okay, so we need some base units here. And the base units for the metric system are the meter, the liter, and the gram. The meter, the liter, and the gram. Meter is a measurement of length. Liter is a measure of volume, which is the amount of space an object takes up. And gram is a measure of mass. Okay, so now I'm going to show you how to use this metric conversion chart to easily convert back and forth between metric units. You'll notice across the top it says King Henry died unusually drinking chocolate milk. I learned this in school as King Henry doesn't usually drink chocolate milk, but hey, use whatever works for you. So King Henry doesn't usually drink chocolate milk, or King Henry died unusually drinking chocolate milk. Each one of these letters stands for a prefix. So the K in King stands for kilo, the H in Henry stands for hecto, the D stands for deca, the U in unusually, or usually, depending on which one you're memorizing here, usually stands for unit, drinking is D, deci, chocolate, C, centi, and milk, M, which is milli. Now remember, there were 4 I told you needed to know. I said you needed to know kilo, deci, centi, and milli. Okay, so these are the ones I'm going to show you how to use on the next page. We're going to come back to this page here in a minute. And now we're going to continue talking about measurements. So we said volume is a measure of the amount of space an object takes up. For solids, we usually use the cubic meter, which makes measuring a cubic object, solid object, super simple. If we're measuring the volume of a liquid, we typically use the liter. Now, I know, again, that we grew up here in America where we use gallons, but you should be familiar with the liter if you think about it. A lot of us buy pop at the grocery store, right? What do they sell pop in? Well, they sell it in cans, bottles. They also sell it in 2-liter bottles. And in some instances, 1-liter bottles. So, for example, you can buy a 1-liter bottle of Mountain Dew. So if you think about it, you should be able to picture a liter in your mind and have a general idea of what a liter is like. Okay? Now, what the heck do we do if we don't have a cubic solid or a liquid and we need to know its volume? So is anybody familiar with the phrase eureka? Well, more than 2,000 years ago, King Hiero II of Syracuse asked the Greek mathematician Archimedes to determine the amount of silver in a royal crown. Though the crown appeared to be made of gold, the king suspected that the goldsmith who he commissioned to make it might have replaced a portion of the gold with silver. The king told Archimedes that he was not allowed to damage the crown in the process of determining whether or not it was pure gold. So Archimedes was kind of at a loss. How in the heck was he going to figure out if the king's crown was pure gold? Well, he was taking his bath one day, and he noticed that his bath, which had been filled up too full with water, had overflowed onto the floor when he climbed in. And that's when the answer hit him. He realized that when he climbed into the bathtub, the amount of water that spilled over to the side was equal to his own volume. So he realized that a crown made of pure gold would displace more water than one would made up of an alloy of lesser weight. So at that point, he leapt out of his bath, ran stark naked out into the street, shouting, "Eureka! Eureka!" which means, "I have found it." Which, you'd have to understand the times in order to understand why he was so excited about that. See, if you failed the king and you didn't figure out how to determine whether or not the crown was pure gold, he might have your head taken off. So, Archimedes was pretty excited to figure this out. And believe it or not, we still use this method today, 2,000 years later. If you go to a fancy gym these days and you want to know your body composition, in order to determine that accurately, they need to know your volume. Well, human beings are kind of lumpy and bumpy. We are not cubic-shaped solids. And the best way to this day to determine someone's volume accurately is to fill up a tank of water, make them hold their breath, measure the volume of the water, have them jump in, measure the new volume of the water. That is still, to this day, how we determine the volume of a human being. So, okay. So we have King Henry doesn't usually drink chocolate milk. Okay, and U is the unit. This is the meter, the liter, or the gram. Now, let's just say we want to convert 12.91 kilometers into meters. How do we use this little chart? Well, here's kilometers. This is our starting point right here. We want to get to U, which is our unit, meters. We're going to look and see how many places did we jump. 1, 2, 3. 1, 2, 3. That is 3 jumps to the right. So we're going to take our decimal point and move it 3 places to the right. 1, 2, 3. So our new unit is 12,910 meters. Okay, how about if we want to convert that 12.91 kilometers and we want to convert it into centimeters? Okay, same starting point, but we want to go from kilometers to centimeters. Once again, we're going to have our chart here, KHDUDCM. We are going from kilometers to centimeters. So how many jumps? 1, 2, 3, 4, 5 jumps. 1, 2, 3, 4, 5 jumps to the right. So we're going to take our number, 12.91, and move it 5 places to the right. 1, 2, 3, 4, 5. So our conversion is 1,291,000 centimeters. 1,291,000 centimeters. Okay, let's try another one. Let's make some room here. Okay, how about, let's see here. This thing does not erase very well, does it? Come on. There we go. That's a little better. Okay. All right, how about another example? Let's convert 349 centimeters into meters. Okay, so now we are going from, come on, why won't this erase? Here we go. Okay, so now we are going from centimeters to our unit. So we're going from here to here. That is 2 jumps. 2 jumps to the left. So now we're going to take our number and we are going to move the decimal point 2 places to the left. 1, 2. So our new number is 3.49 meters. This is a super easy way to convert back and forth between the metric system if you become familiar and comfortable with it. Since we use this system exclusively in chemistry, I strongly recommend you become comfortable with this system. So let's go back to our Let's try an example of this. If we have a graduated cylinder, which is a common laboratory piece of equipment, and that graduated cylinder initially has water in it at a level of 48.6 milliliters of water. And we drop a golden crown in the water, and the water level volume increases to 61.2 milliliters. This is an awfully tiny crown because I couldn't afford a whole lot of gold. What is the volume of the crown? So in order to determine this, we are going to take the volume of the crown and the water, 61.2, and we are going to subtract the initial volume of the water without the crown, which was 48.6 milliliters. So volume of crown plus water minus volume of water should give us volume of crown. So let's see here, 61.2 minus 48.6 is 12.6 milliliters. Itty bitty crown. Oops, I forgot the 0.6. 12.6 milliliters is the volume of our crown. Why in the world do we care about volume? Well, volume is something that relates to density. The density of an object is the ratio of its mass to its volume. The more closely packed the molecules are, the higher the density. The further apart the molecules, the lower the density. Density is an extraordinarily useful property, and it's something that we can use even today to determine real-world problems. So, for example, If you're doing yard work one day and you find an old rusted coffee can full of coins that appear to be made of silver, you want to know, are they really, right? Did you hit the jackpot? Super simple way to figure it out, whether or not they're pure silver. And that is to determine the density of the coins. Because all metals have a density. If you can match the density of your coin to the density of a metal, you will know whether or not your coin is pure silver. Densities are usually expressed in grams per milliliter or grams per centimeter cubed for liquids or solids, and grams per liter for gases. So let's check it out. Let's see if our coins are actual silver. So we're going to go in the lab and we're going to weigh one of those coins. And when we weigh it, we determine that it has a mass of 15, not 1.51. That would totally mess everything up. Has a mass of 15.1 grams. Then we're going to take our graduated cylinder here. We're going to put some water in it. Okay. Initially, we're starting out with 25.3 milliliters of water. When we put the coin in, the water level rises to 27.2 milliliters. Okay. In order to determine the density of the coin, we need the formula. Density equals mass over volume. We've determined the mass. What is the volume of the coin? Well, the volume of the coin is the volume of the water plus the coin, which is 27.2, minus the water, which was 25.3, should give us the volume of the coin. 27.2 minus 25.3 is 1.9 milliliters. So now we are ready to set up our formula. Density equals mass over volume. So we have 15.1 grams divided by 1.9 milliliters. So 15.1 divided by 1.9 tells us that we have a density of 7.95 grams per milliliter. So over here we have some common densities. You might notice that those densities are given in grams per centimeter cubed. 1 centimeter cubed is equal to 1 milliliter. So we can say that our density is 7.95 grams per centimeter cubed. Does this match silver? Alas, no. Silver is 10.9 grams per centimeter cubed. We do not have a coffee can full of coins that are silver. Instead, if we look, we have a coffee can full of coins that are made of iron, which is essentially worthless. So we did not hit the jackpot. Sad, sad, sad. Okay, let's move. Okay, so the third part of any measurement. Remember I said at the very beginning of this lecture that there were 3 important parts to the measurement. There was the number itself, the unit, which tells you what you're measuring, and then finally there was the degree of uncertainty in the measurement. So all measurements have some uncertainty in them. And we need to know how much uncertainty so we can report our measurements properly. In order to determine how much uncertainty is in a measurement, we need to understand something called significant figures. Significant figures are the digits in a number that we use to express that number to the proper amount of accuracy. And we need to have a set of rules to determine how accurate a particular measurement is. And we use these rules universally. So again, learning these rules for your chemistry class is going to help you in biology, it's going to help you in physics, it's going to help you in math, it's going to help you in a lot of other classes. Okay, so how do we determine this? First are the rules for significant figures. Rule number 1. All digits that aren't 0 in a measurement, including the digit that has the estimated part, are significant. So if you are not a 0, 1 through 9, you are significant. Okay? Now, what if you are a 0? Right? What if you are 0? Well, there are 3 kinds of zeros. Okay? And what kind of zero it is determines whether or not it is part of the significant figures in your measurement. The first kind of zero is a leading zero. Leading zeros are the zeros that start out a number. So if your number starts out 0 point something, that zero is a leading zero. Leading zeros are never significant. So when you're looking at your measurement and you are determining the uncertainty, you ignore the leading zeros. And it does not matter how many leading zeros there are. All the way up to the first number that isn't 0. All of those zeros are considered leading, and they are never, ever, ever, ever significant. The second kind of important zero is called a captive or sandwich zero. Those are zeros that are in between two numbers that aren't 0. So for example, 204. This zero is a captive or sandwich zero because it is bracketed on either end by two numbers that are not 0. Okay. These are all captive zeros because they are bracketed on either end by two numbers that are not 0. Captive zeros always count. So as long as you are sandwiched by two digits that are not 0, you count. So we have two rules about zeros so far. Leading zeros never count. Captive zeros always count. Now we come to the third kind of zero, which is not an absolute. Trailing zeros are zeros at the end of a number. So any zero that comes after the last non-zero number is a trailing zero. Trailing zeros only count if there is a decimal point. Now, I want to be really clear that it doesn't matter where the decimal point is. If there's a decimal point anywhere in the number, the trailing zeros count. So for example, if I were to add zeros onto this number here, I have a decimal point here. So these first 1, 2, 3, 4, 5, 6 zeros are leading zeros. They never count. And these last 4 zeros are trailing zeros, and they count because there is a decimal point. So I want to do some practice with this because I know this is a topic that can cause students some difficulty. So let's take a look at example 5. We are going to classify the zeros as leading, captive, or trailing, and we are going to determine the number of significant digits in each number. So 3090, what kind of a zero is the first zero? Well, it's between the 3 and the 9, which makes it a captive or sandwich zero. And this zero here, the second zero, is at the end of the number, so we would call that a trailing zero. So we have a captive and a trailing zero. Now, how many significant figures are in this number? The 3 is significant, the captive 0 is significant, and the 9 is significant. The trailing zero depends on whether or not there's a decimal point. Since this number has no decimal point, that 0 does not count. And we say that this particular measurement has 3 significant figures in it. Okay, let's take a look at the second example. These first 4 zeros start off the number. Therefore, they are leading zeros. So we have some leading zeros. And then we have a 7 and a 6, both of which are non-zero digits, so they are significant. Then we have this 0 here. That 0 is sandwiched between a 6 and a 1. So that is a captive or sandwich 0. So that's a captive. And then finally, we have the 0 on the end of the number here. That is a trailing 0 or a 0 at the end of the number. So determine the number of significant figures. The first 4 zeros are leading. Leading zeros are never significant, so we don't count the first 4. The 7 and the 6 are significant. The captive zeros are always significant, so we count that. The 1 is significant. And the 0 on the end is a trailing 0, which is significant if there is a decimal point. There is a decimal point in this number. So that 0 is significant. So we have 1, 2, 3, 4, 5 significant figures in this measurement. The only digits not significant were the first 4 zeros. Okay, let's look at our final example here. We have a 1, which is significant. We have 2 zeros between a 1 and a 4. Those are sandwiched between the 1 and the 4. So those are captive or sandwich zeros. They are significant. We have a 4, which is not 0, so that is significant. We have another 0 between the 4 and the 5, or sandwiched between the 4 and the 5. That is significant. We have a 5, which is significant. And then we have 2 zeros at the end, which are trailing zeros. They are significant if there is a decimal point. There is a decimal point in this number, so those trailing zeros count. Therefore, every digit in this particular measurement is significant. So we have 1, 2, 3, 4, 5, 6, 7, 8 significant figures in this measurement. The 1, the 2 zeros, the 4, another 0, a 5, and 2 more zeros. 8 total significant figures. Again, this is something you need to become comfortable doing on a regular basis, determining the number of significant figures in a measurement. We have multiple videos on this. I suggest if you're not comfortable watching them. Okay, example 6. What if you want to write the number 9 million with 2 significant figures? Could you accomplish this without scientific notation within the rules given so far? So how many significant figures are in the number 9 million as it is written? Well, the 9 is significant because it's not 0. What about the zeros in this particular number? They are at the end of the number, so they are trailing zeros. Trailing zeros are significant if there is a decimal point. There is no decimal point in this number. So right now, we have 1 significant figure. Okay? If we add a decimal point to this number to get us to 2 significant figures, what happens? We had a decimal point here. Now, those trailing zeros become significant. So now we have gone from 1 significant figure to 1, 2, 3, 4, 5, 6, 7. So we've gone from 1 significant figure to 7. Is there any way to get this in 2 significant figures? Well, not as written. However, the beautiful thing about scientific notation is that every digit written in scientific notation is significant. So let's think about how to put this into scientific notation. Remember that I said that we place the decimal point immediately after the first number, not 0. So our decimal point is going to go here. So we have 9.0. Now, how many places did we move this? 1, 2, 3, 4, 5, 6. So 9.0 times 10 to the 6. If we are looking at significant figures, we have a 9, which is significant, and we have a trailing 0. However, because we're in scientific notation, we will always have a decimal point. So that 0 is significant. So 9.0 times 10 to the 6 contains 2 significant figures. What if I wanted to write this with 3? 9.00 times 10 to the 6 is that same number now with 3 significant figures. There are never any leading zeros in scientific notation, since we always place the decimal point immediately after the first number, not 0. So scientific notation is wonderful because all of the numbers in scientific notation are significant, which makes your life much easier. So again, become comfortable with scientific notation. It's a wonderful tool to use in the sciences. Okay. So, how do we know how many significant figures to write? So, for example, does your car get 34.7 miles per gallon or 34.6789500000321 miles per gallon. So how do you know? How do you know what to write? Well, there are two sets of rules here. One is for multiplication and division, and the second is for addition and subtraction. So if you are multiplying and dividing numbers together, you need to know how many significant figures your answer should have. Okay? So if, for example, you were to take 4.36 and put that into your calculator, and then multiply that by 0.00013, your calculator display would give you 0.0005668. Now, it is important that everyone in the science report their measurements the same way. So if you were going to put this in your calculator, some of you might on the test give me the answer 0.000567. Some of you might give me the whole thing. Some of you might say it's 0.00057. Some of you might say 0.0006. Which one is the correct answer? Well, since we don't want everyone just making up their own minds as to where to round, we have rules. When we multiply or divide, we round our answer to the least number of significant digits. In our original numbers that we multiplied, we had 4.36, which has 3 significant figures. There are no zeros, so all of the digits are significant. So we have 3 significant digits. In the second number, we had 0.00013. Those first 4 zeros are our leading zeros. Leading zeros are never significant. So the 1 and the 3 are the only 2 significant digits in the measurement. So, to conclude, we had a number with 3 significant digits and a number with 2 significant digits. Our answer should have the same number of significant digits as the one with the fewest. The fewest is 2. So the correct answer in this situation would be 0.00057, not 0.006 or 0.000567 or 0.0000568. Okay? How about if we try a division? 12.300 divided by 0.0230 gives us in our calculator of 534.78261. Again, what do we report? Do you report that whole number? Do you report 534.7826? 534.783? 534.78? I mean, what do you report? Well, the first number, 12.300, has 1, 2, 3, 4, 5 significant digits. The zeros in this number are trailing zeros. There is a decimal point, so they do count. So we have 5 sig figs. In the second number, the first 2 zeros are leading zeros, which never count. The final 0 is a trailing 0, and we have a decimal point, so it counts. So we have 5 sig figs and 3 sig figs. Therefore, our answer should have 3. So we are going to round 534.78261 to 535. Now, I know some of you are not really familiar with rounding. It may have been a while since you've done this. So there is a great little mnemonic to help you remember this. It says find the number, look right next door. 5 or more, raise the score. 4 or less, let it rest. So in our previous example, we had 534.78261. We wanted to round to 3 digits, so our right next door is a 7. That 7 is 5 or more. So what are we going to do? Raise the score of the last number. So that 4 becomes a 5, and we have 535. Okay? What if we were rounding to 2? Right? What if we needed 2 sig figs instead of 3? So let's take a look at what that would have been. 1, 2. right? So look right next door, that's a 4. It's 4 or less, we're going to let it rest, meaning we're not going to touch the 5 or the 3. Now, what happens to that 4? Can we just drop it? No, you cannot just drop the 4. You must replace it with a 0. If you have $534 in your bank account, and I am going to round down, and I round it down to $53, are you going to be okay with that? My guess is no, right? You're probably going to be a little upset about that. So just remember when rounding not to just disappear those numbers at the end, right? They become zeros. Okay, how about addition and subtraction? So that covers multiplication and division. What do we do about addition and subtraction? Well, in some ways, I think addition and subtraction is a little easier because addition and subtraction has to do with decimal places, not significant figures. When we add or subtract, we round the answer to the least number of decimal places. What do I mean by decimal places? So by decimal places, I am referring to the number of places after the decimal point. In this first example, we have 1.457 plus 83.2. This first number has 1, 2, 3 places after the decimal point. The second number has only 1. So our answer should have the least number of decimal places, or 1. So if we are adding this up, in our calculator we would get 84.657, but we only want to report to the fewest number of decimal places. That's this one. So we are going to look right next door. It's a 5. 5 or more, raise the score. So my final answer should be 84.7. In subtraction, it's the same thing. 0.0367 minus 0.004322. We have 4 decimal places in the first number and 6 in the second number. So our answer should have 4. In our calculator, we would get 0.032378. But again, we only want 4. 1, 2, 3, 4. So here's our cutoff. Look right next door. We have a 7. That is 5 or more. So we are going to raise the score. 0.0324 is our final answer. Just real quick, let's practice a little bit of rounding because I know some of you are not comfortable doing rounding. For those of you that are, feel free to skip on ahead here. Okay, we're going to round the following numbers to 3 significant figures. We have 15.4462. We have 1, 2, 3. Look next door. It's a 4. 4 or less, let it rest. So our answer is 15.4. 93.75. 1, 2, 3. Look right next door. 5 or more, raise the score. 93.8. 6.9170. 1, 2, 3. Look right next door. 5 or more, raise the score. 6.92. Okay. What else do we have here? Okay. 92.85. 1, 2, 3. Look right next door. 5 or more, raise the score. 92.9. 69.95. 1, 2, 3. Look right next door. 5 or more, raise the score. So in this case, we have a 9. What happens when we increase that 9? That 9 becomes a 10. So that's a 0. The 1 comes over here. That 9 then becomes a 10. 0, carry the 1. That becomes a 7. So rounded, this is 70.0. How many significant figures are in 70.0? These two zeros are trailing zeros. When do trailing zeros count? Trailing zeros count if there is a decimal point. Is there a decimal point in this number? Yes, there is. So we have 1, 2, 3 significant figures. So our rounded answer, 69.95, is 70.0. Okay, and then our final example, we're rounding to 2 significant figures. We have 442,000. Okay, 442,000, 1, 2. Look right next door, 4 or less, let it rest. 4, 4. What do we do with this? We have to put a placeholder 0 in. 442,000 rounds to 440,000, not 44. So 440,000. What kind of zeros are these? Trailing zeros. When do trailing zeros count? Trailing zeros count only if there is a decimal point. There is no decimal point. So we have 2 significant figures in this number. Okay, so finally, let's just talk briefly about the difference between precision and accuracy. Accuracy is how close you are to the real result. Precision is how close your results are to each other. So say, for example, I give you a beaker of water and a thermometer, and I ask you to measure the boiling point of water. We know from thousands of measurements that water boils at 100 degrees Celsius. If you take 3 measurements and your thermometer tells you that the water boils at 99.6, 99.8, and 99.5 degrees Celsius, I would say that your thermometer is fairly accurate. So again, accuracy is a measure of how close your results are to the true results. Precision, on the other hand, is how close your results are to each other. So say we repeat the same experiment, but now with a different thermometer. And this thermometer tells us that our water is boiling at 89.9, 89.8, and 89.9 degrees Celsius. Our results are precise. They're very close to each other, but they are not accurate. They're not even close to what the true result of 100 degrees should be. So measurements can be accurate but not precise. They can be precise but not accurate. They can be neither accurate nor precise, or they could be both accurate and precise. We're scientists. We're looking for accurate and precise. Why? Well, let's say, for example, that you work for a pharmaceutical company and you are a quality control chemist. You are checking the accuracy and precision of 3 different machines that are meant to dispense 10 ounces or 296 milliliters of cough syrup into storage bottles. So we're going to use each machine to fill 5 bottles. And then we're going to determine the actual volume that was dispensed, obtaining the results in this table over here. So my question to you is, which dispenser is accurate? Which one's precise? Are either of them? Are neither of them? So let's take a look at dispenser 1. Dispenser 1 is supposed to dispense 296 milliliters of cough syrup. On its first tryout, it dispenses 283. Then 284.1, 283.9, 284.0, and 284.1. Looking at those measurements, I would say they're all close to each other. So they are precise. However, they're not accurate. We're a good 10 mils off of what we should be at. So I would take that dispenser, send it back to the manufacturer, and ask them to adjust it. It's precise, but it's not accurate. Dispenser number 2, 298.3, 294.2, 296.0, 297.8, 293.9. I would say it's kind of close to being accurate, but it's not very precise, is it? Those measurements are not close to each other. You've got a 298.3 on the high end and a 293.9 on the low. So while it is closer to the original 296, the measurements are not close to each other. So you never know what you're going to get with that dispenser. I would definitely send that dispenser back to the manufacturer. Dispenser number 3, we got a 296.1, 95.9, 96.1, 96.0, 96.1. I would say that dispenser is both accurate and precise. And if I needed life-saving medication, I'd want it from dispenser number 3. So again, that is the difference between accuracy and precision. And that is where we are going to stop for today. On Monday, we are going to pick up with dimensional analysis. Thank you very much for listening.